Welcome to our presentation on Children Map project. My name is Yuhui Wu, and I'll be presenting today with Junfei Huang. This project focuses on building a mapping tool tailored for USC and its surrounding areas. Here is an overview of all the functions we have used in our project. Let's start with autocomplete feature, which allows users to type a partial location name, returning case-insensitive matches like CHI, suggesting Chipotle or Chipotle. The algorithm compares input prefixes with all location names. Next is find the location. Where users retrieve the latitude and longitude of a specific location, we enhance it with the edit distance feature, which corrects typos. For instance, typing target suggests targets, using dynamic programming to calculate the closest match. We also implemented a location category feature to list all categories like restaurant or bank without duplicates. Other than that, users can also retrieve all locations in one certain categories. Here's how it works. Once you input field, it will output all the location IDs which have that kind of attributes, and also it will plot them on the map for easily visualization. The regex search features lets users search with patterns like CHI to match locations starting with CHI. It validates regex inputs and returns results or notifies users of invalid queries. Finally, the shortest path calculation identifies the best routes between two locations using Dijkstra or Bellman-Ford algorithms. Dijkstra is faster, but supports only non-negative ways, while Bellman-Ford handles negative ways but is slower. For example, here we can see that Dijkstra runs only in 36 milliseconds, while Bellman-Ford takes much longer time.
We also compare three shortest path algorithms. Dijkstra is significantly faster than both versions of Bellman-Ford. For example, from Ralph's to Chick-fil-A, Dijkstra took 85 milliseconds while Bellman-Ford took over 11,000 milliseconds. For item 7, we perform circle detection. We first enter coordinates to define a subgraph and detect if a circle exists. The program found a circle in 28 milliseconds. This is then visualized on the map, where red line shows the circle path, demonstrating our algorithm's capability in real-world mapping. The next is typological sort. Tommy Children needs to deliver food while following constraints. After inputting the locations and dependencies, the result shows the optimal order as Ralph's, Chick-fil-A, and then KFC, computed in 0 milliseconds. The map here shows the feasible route with green arrows indicating the delivery sequence. For item 9, we tackle the traveling salesman problem using brute force backtracking and 2opt. First, for 8 locations, brute force took 65 milliseconds while backtracking took just 23 milliseconds. Then, using 2opt, we solve problems for 6 locations in 0 milliseconds, demonstrating notable improvements through optimization. Item 10 is Found Nearby feature. We first searched our supermarkets near Ralph's within a 5-mile radius, finding 3 locations in 2 milliseconds. Then, for restaurant near KFC, we found 5 results within 10 miles in 3 milliseconds. The visual map clearly indicated the proximity of these points from KFC and Ralph's respectively, illustrating the ease of finding nearby places. In item 11, we compute the shortest path to visit all locations in a given list. After providing the location data, the program outputs the sequence covering a total distance of 1.86 miles in 141 milliseconds, effectively minimizing travel distance. Lastly, in item 12, we determine if a path exists between 2 locations given gas tank constraints. In first example, traveling from Target to Ruffles with 0 gallons unsurprisingly resulted in no. In the second example, multiple queries showed that with small gas tank sizes, paths are possible between Trader Joe's and KFC to Popeyes, but not from Popeye to boba time. The system effectively evaluates each scenario, providing clear results. That's all about our children map project. Thank you for your patience.